Welcome back to the second part of the image processing and image analysis workshop. In this part, we will now start to actually process the image and get to segmentation. To begin with, we will start a new geodict to pick everyone up that might have gotten lost along the way. So if you have geodict still open, close it and just start a fresh instance. We again get the license expiring warning. And now to load the file, you can either click down here where it should still list the file we just saved, or for people that might have not saved the file, we go into import geovol, click on browse. We are back in our project folder. In here we can either load it the file we saved, or if you missed to save the file, you can go into the results folder. There's also the file contained. We open it, get into the import settings, and as you can see now all the parameters are filled in automatically, even the voxel size. And then we click into image processing to get back into import geovol. Now everybody should be back in the image processing user interface, and you should see the same view as it is visible here. As we discussed earlier, if you zoom in here, see that the image is very noisy. With the segmentation overlay, it is very obvious that there will be a lot of artifacts at the boundary of the grains. So the first step we want to do is to get rid of the noise. To do this, we will use the non-local means filter. The non-local means filter is located on the left side under the image filters entry. It is the first entry. To set the parameters for the non-local means filter, we will use the preview. The preview allows us to vary various parameters and see the effect it will have on the scan. If we click the preview button, we get this window. At first there is no preview visible. Now we will change some parameters here. First of all, I want to see a big portion in the Z direction as it will be plotted vertically and we have a lot of space there. And then I will first of all vary the patch radius. So I set the patch radius to vary from 1 to 4, for example. And I also set the strength to be used to 0.4, because 0.5 is usually already quite strong. Then I click the update button. And as you can see, it's doing some calculations. It takes a bit of time to calculate the bigger patch radius. And now we have here some images. To see them correctly, we'll make the window big. And we also increase the zoom to maybe 200%. So now we don't see a lot because the gray value range is not set correctly. So we reduce the maximum gray value. And you can see now the image gets more clearer in here. So we can basically set the same value we have already set here in the main interface, so 0 and 11,000. Now we can see that the effect that the non-local means filter will have depending on the patch radius. First image is always the original image. And after that, we get the image for patch radius 1, 2, 3, and 4. As you can see, there isn't that much of a difference here. So if I increase the zoom again to 400%, you can look a bit more into the details. And as you can see, it doesn't change a lot. You can also get a preview of what the effect on the segmentation will be by increasing the threshold visibility up here in the left. I do this now, and first of all, we see there isn't a really useful preview because our threshold is set too high. Now we turn down the threshold, get to area where everything is solid, and then We enter a value around 8000. We get a first preview of the thresholding, and we can see already the original image. We have all these holes and noise in the pore space, and in the filtered images there isn't that noise is gone. So as you can see, for the thresholding, the effect isn't very big, so we'll just go with the default patch radius of 1. The next thing we will vary is the window radius. So we do again a window radius maybe from 2 to 4. We calculate it. Again, have to wait a bit. And now we have the preview for the various window radius. We can again turn down the threshold visibility to see the original image and the filtered images next to them. You can see the image gets a bit blurrier for the higher window radius. So we will go with a window radius of 2 for our example. And finally, we can also see the impact of the strength of the filter. So we vary the strength from 0.1 to 0.5 steps of 0.1. Again, calculate the image. And then we can see for the strength of 0.1, there's still, the image is not really nice. There's some noise still visible. And for the higher strength, it gets less noisy. And for a very high strength of 0.5, or if I turn it higher, for example, 0.8, the image starts to get a bit blurry. So we will go with 0.4. And by clicking on this preview, you see now there is a square set on the image. And then clicking close, the parameters we just selected are entered into the interface. Now we can apply this filter to the image by clicking the apply button. We click the apply button and the image filtering happens. So for me now this was really fast because I have a fast GPU in this computer. Maybe for some of you it will take a bit longer because I don't know what computers you are using right now. One thing you can see down here in the histogram, there is already some of the stuff that was here on the left is gone. And also we can now again increase our lower value of the gray values. We have a better separation of the two faces. So what you usually see in two-phase CT images is that you have a peak, then you have a kind of a valley, and then you have another peak. At least that's the case if you have a nice, well-behaved CT scan. Of course, there's also the cases where this is not really true. And one nice effect of the non-local means filter is that it usually increases the separation of these two peaks. So I hope by now everybody has finished computation. If no GPU is available, the computation might take a bit longer as it is then executed on the CPU, but the most GPUs are supported and should work fine. The next step in our process will be segmenting the image. Segmenting the image is necessary to be able to do more advanced computations on it. So for example, to define the size distribution of the grains, we need to first define what part of the image is part of the grains and what part is part of the pore space. So we go over here into the segmentation and labeling tab. And then by default, the image segmentation entry should be opened. And this is where we can do, where we can apply various methods to segment the image. First of all, now it is important to put the visibility of the segmentation up here to some medium value, because now we want to see what we will be segmenting. And also a very nice option is the outline switch here. That will turn the segmentation from an overlay mode to something where only the boundary is colored. So if I zoom in here now, I see there's a red border around the crane defining the boundary of the ID, material ID 1. So if I pull this a bit bigger here, you will see material 2 ID 1 is our solid, and material 1 ID 0 is our pore space, and it's colored in white, and material ID 1 is colored in red. And yeah, next to the red line, you see the border of the pore space as a white line. If you have more than 2 faces, then you of course will have to, there will be more than 2 colors. So now for this example, we will go with a single threshold because there's only 2 faces visible. There's the pore space and the solids, the grains. And we can also turn back the outline to an actual overlay. To segment the image, we have multiple methods at hand. So first of all, for the image segmentation function in here, we have the option between a single threshold, multiple threshold, and watershed-based multi-phase segmentation and entrainable AI-based segmentation. For this example, we will use the single threshold segmentation. Later on, we will do a second example where we use the AI segmentation. There are also other segmentations available, like the Van Zalker or local Otsu filter that use local measurements to calculate local thresholds. There's also the option in here to do watershed image labeling, where you directly create object indices out of the gray value image, and also the option to create a surface triangulation. For the single phase segmentation, you can select between multiple methods to define the threshold. The first method is just using a manual threshold. The second method is the Otsu threshold, where based on the histogram an ideal threshold is calculated. There's also the option to use k-means clustering to calculate this threshold. The results are often very similar to the Otsu threshold, and you can also define use hysteresis thresholds. Let's see how the threshold influences the segmentation of the image. If we switch here to the manual threshold method, by default the value calculated by the Otsu threshold is set. You can see it is placed exactly in the middle between the 2 peaks at the valley of at the bottom of the valley between the 2 peaks. You can change the threshold by pulling on the slider. By increasing it, you can see the grains get a bit smaller and they also disconnect. By decreasing it, you see the grains getting bigger and they are also more connected. If we go with the value very high, you'll see the grains falling apart. Let me pull this a bit bigger here. For example, if I enter now a value of 8000, we have already a quite nice segmentation. If we go to a value of 6000, then we have way too much and we start to get some speckles in the pore domain. So for this example, we will use the Otsu threshold. The convenient thing about the Otsu method is that it is able to calculate a threshold relatively reliable for CT scans that have a certain quality. So if you have this separated peaks in your CT scan, you can usually go with the Otsu method. See now the slider for the threshold is disabled. Below it we can see the volume fraction of material ID 0 and 1. so for the pore in our solid, and it's calculated for, so there's 60% pore and 40% solid in the domain. If you are in the manual threshold mode and pull on this slider, these values will automatically update. So if you know the volume fraction, for example, the solid volume fraction of your sample, you can also adjust the threshold in a way that it matches this value. So the next thing we have to do is define the materials. By default, they are just labeled pore and manual. For this example, we know, okay, there's just a pore, and for the material ID 1, our solid, we know this is NMC. So we click on that button next to material 2 ID 1 and scroll to NMC in this database and press OK. Now Geodict has some material information associated with this material ID, for example, the conductivity of the material that can later on be used in simulations. If you have planar material, like a sheet material, for example, you can also define the density of your solid material here. And then you get the grammage calculated in a plane. So here, by default, it's the XY plane. You can also select another one. So if you know the grammage of your material, you can also use this value as an orientation for your threshold. Now, before we create the actual segmentation, up here we can define the result file name. When we create the segmentation, Geodict will write a result file containing information about the filters we have applied during the process and also some statistics on the material. This is very useful to have your results reproducible. So we will now name this file cathode segmentation GDR, because later on we will also create some other result files and we don't want them to collide. So now we can click on the create segmentation button and Geodict will do the segmentation. As it's just a single threshold method, it is really, really fast. Now what has opened here is the result file. You can see there is the method we used, the threshold value that resulted from that method. There is the image filter that we used and some information on the structure like the porosity and so on. For the image filter, the map also contains the parameters that were used. So if I go in to the map view, I can see here image filters, image filter 1, and there are the parameters that we have used. So this file really makes your segmentation process reproducible. So now we are still in the image processing user interface. We can close this dialog by clicking the button down here. And now we are back into the main Geodict user interface. You can see now that there's in red is the segmentation, and there's still in the background now only visible in black the gray value image. We can, for example, disable the structure, then we can see the gray value image. So now the color map is a bit bad, so I will change it in a way that it is visible better. Now we can see the grains again, and we can enable and disable the structure and see the result of the segmentation. We can also do this in 3D. We open the 3D view. We again have our original CT scan, and we can enable the structure to overlay with it. And then, for example, we can clip away parts of the volume field, and we can see the structure without the volume field. So now, if we would not be fine with the segmentation and we wanted to change something, we can right-click here on the left where gray value images is. We can right-click that entry and open in image processing dialog. This will open back up the image processing dialog, and we could, for example, change our threshold. That's not important in this case, as we are fine with the segmentation, and we can just click the discard image in the bottom. Yep, it warns you that you will lose this gray values you have here. And now we only have our structure in Geodict. To make it a bit more visible, we will enable outlines in Halo. So now we can see the cranes better. If for some reason you got lost along the way, you can click on the button up here to open a structure and go into the results folder and into cathode segmentation and load structure GDT to get the same structure that we have created right now. Now that the structure is segmented, we can start analyzing it. To do so, we click on the Analyze button up here. In the list appear all the modules that allow to do geometric analysis on the structure. So there's no flow simulation in here. This stuff is in the Predict menu. We will start off with a simple analysis of the solid phase distribution by clicking on MATDICT. In MATDICT, we have many analyses at hand. For example, we can do a 1D statistic where we just get a density distribution in each layer. We can get a 2D projection of the density. We can also do stuff like calculating size distributions. We will for now just do a simple 1D statistic. So we select in the first combo box material statistics and in the second one 1D statistics. Now if we go in here, we can select in which direction we want to do the analysis. We will go with the Z direction. The background mode POR means that POR is defined as background and it will analyze all the materials that are not POR. So in our case, material ID 1, the NMC. And then we can also set what kind of media we expect. So if we know we have a homogeneous media, then there will be a fit only for a homogeneous medium, but we can also say we have a gradient in there or an empty inlet or a non-empty inlet. So in this case, everything looks pretty homogeneous. So we click on homogeneous media, click OK. And then down here, we click on the Run button. Again, next to it is the Help button. So if you want to learn on all the other functions you have in this module, you can click on the Help button and get directly to the user guide. So now click the Run button. And we will get a result really fast. Now we have the mean solid volume fraction. That is the value calculated for each layer. We get the thickness. And also in the plots, we can see, okay, this is the mean value that was estimated, and there is some variation around this mean value. But overall, it's pretty homogeneous. Maybe there is a slight tendency to be a bit less dense in the upper layers, in the lower layers, sorry. For our final geometry analysis, we will now analyze the cranes in the structure. So we go back into the main menu and select the Crane Find module up here. In the Crane Find module, we have the functionality Identify Cranes. With this functionality, it is possible to label each crane in the structure individually. So if you would only analyze the connected components of this material now, everything would be connected. Maybe there are some cranes that are disconnected, but most of them are connected. With Identify Cranes, these cranes are separated into individual cranes, and for each crane an analysis is run that yields, for example, the aspect ratio and the diameter of the crane. Also, each crane is converted into an analytic representation. To run this analysis, we go into Crane Find, select Identify Cranes, click on the Edit button for the options, and we can see the options we have in here. So now, first of all, there's a minimal crane diameter that can be entered, and we will want to increase this value. I will show you how you get to this value. So close this dialog again, go into the 2D view. Now search for a small crane For example, this one right here in the middle. And if you now hold the shift button, click and hold your left mouse button and move it around here, you can get this measurement tool. Now you see you get this context menu. You can, for example, open the adjust voxel length dialog, then you see the length in voxel. So now the thing we measured here is 13 voxels long, or in real units it's 5.4 micrometer. You can also make this measurement more precise by zooming in. So hold the right mouse button and move the mouse down. Now you are zoomed in, and you can move this around, for example, to put it right on the edge here, and you get the length of 5.4 micrometer of this crane. So now we know this is pretty much a very small crane already in here. So if we go back into 3D and go into identify cranes, we just use half of the value we measured. So that was like 13 voxels. You can also switch this to meters. And to be sure that we don't remove some cranes that we actually wanted to analyze, we put half of the value we measured. This mainly speeds up the computation a bit. We also make sure that this checkbox right here, remove crane fragments at the domain boundary, is checked. This will remove the cranes that are cut by the domain boundary, so they don't mess with our statistics. In the output options, we enable saving the crane size distribution. This will output a volume field where in each voxel the corresponding size of the crane that occupies this voxel is saved. We also changed the name from result file from identify cranes to cathode underscore identify cranes. Now we press OK, and then we press the run button. So this computation now will take a bit longer than the previous ones, as the process is a bit more complex. There are more than one step that is running, and that takes a bit of time. In the end, we will get a result where each voxel in the original image is assigned to a specific crane, besides the pore space, of course, and also all the statistics for the cranes. So there will be size distributions, orientation for each crane, and so on. So now we are nearly done. Now we are done, and we get another result file opened up here. I will make this big now because it's a very complex result file. So the first result up here is the number of cranes and the number of contacts between the cranes in the structure. And below it, we get a lot of statistics. For example, diameter distributions, the orientation of the cranes. But the first thing we want to look at now is not actually the plots, but the crane visualization, and in here, the crane index image. So we click on load G32 here and load up the result. Now we minimize this. Now we see in 3D the colored indexes of the individual cranes. So here are now, I think, 32 or 64 different colors that are randomly assigned to the indices. And we also see there are no cranes touching the boundary, and we only see the complete cranes. This is because of the remove boundary cranes option we enabled in the options dialog. If for some reason this takes a bit longer on your computer to compute, you can cancel the process, click on the bottom open result file up here, and go into the results and open the cathode identify cranes result that was delivered with the input data for the workshop. We can also look at this in 2D. You can see here the cranes that are touching are nicely separated into different cranes. So now we go back into the result file, make it again big, and what we also can load is the grain size distribution. That's the second button here, load GSD. Click it and minimize again. Now that first of all looks a bit confusing because we still have the gray value color map from the CT scan set, but we can just switch in the volume field tab at the color map button here to default. And we can disable the visibility in ID 0, so in our POR, because we only analyze the solid material. And now we see there's the 0 grains out in the outside are the ones that we didn't analyze. And in between, we already see the other grains. If we now increase the clip value we have up here in the middle, we only see the values that have the grains that have a diameter bigger than 0. And you can see there are small grains in here that have a diameter of 5.6 micrometer, or up here a really big one with a diameter of 16 micrometer. We can also see this in the results. If we go to results and into the plots, and then we can have a look at the diameters, and then we can see the diameter distribution. And we already see there are like 2 main peaks in here. And there's also a lot of other interesting information you can obtain from here. The same process can also be done for pores. So we can, for example, in this would be able to separate the individual pores and also obtain their size distribution. This will conclude the second part of the workshop. So you are now free to ask questions, and we will resume the workshop in 10 minutes with a new sample to analyze. Thank you.